Okay, so we're asked to find the moment of inertia for a solid cylinder. So just to visualize what that looks like. And then the moment of inertia for any object is this basic formula. But since we cannot integrate r when we have a dm here, we have to replace the dm with the dr so that we can integrate in terms of r. The way we do this is by using density equals to mass over volume. In this case, it's pi r squared times L, because that's the volume of a solid cylinder. And then isolate for m by multiplying the denominator up. And then we want dm, so we just derive both sides. And then I would take this whole thing and then replace it into here. So and then we can take these terms out because they're all constants. And then leave it as from 0 to r cubed dr. And then we integrate this. This ends up being r to the power 4 over 4 from r to 0. This simplifies to this. And we don't know density here, so I'm going to replace it with what we found over here. And this will just simplify to r to the power 4 over 4. And we can cancel some things out. So L will cancel. This 2 will cancel with this 4. This R will cancel with this R. And then these pi's will cancel. And so ultimately, inertia will simplify to be m r squared over 2. So we're going to start by setting up net torque equals to inertia of the cylinder times alpha. We can also make true statements. So the net torque is also the only force being applied, which is tension, times the distance from which the force is being applied to the pivot. So in this case, it's r. And then we can set those as equal to each other. And I'm going to expand the inertia to 1/2 mr squared like we found earlier. Leave alpha because we're trying to find alpha, dr. And then this r will cancel out with this r. And for now, I'm just going to leave it as tension equals mr times alpha. 1/2 mr times alpha. And then moving on to the net force of the block mass is equal to the mass of the block times acceleration. But I'm going to expand this into alpha times r because we're trying to solve for alpha. And then the net force is also just Fg, the downward force, minus the upward force. And then we can set these two as equal to each other. Sorry. And then we know T right here, so we're going to substitute that in. And then we want both alphas on the same side, so I'm going to add this one over to that side. So I'm going to rewrite it over here. Okay. And then we're going to plug in the values. Sorry, what? And then this would end up simplifying to be 5.4 alpha on this side. And then on the other side, it's just 29.4. And then the way we would isolate for alpha is dividing both sides by 5.4, which will get alpha equals 5.44. And then don't forget our units. Okay, so linear acceleration for the block is just equal to alpha times the radius of the cylinder. And we found alpha earlier, so we can substitute this in. And then the radius is 0.3. We would get 1.633 meters per second. Okay, for part D, we're going to be using displacement formula equals to 1/2 alpha times t squared. But then it starts at rest, so we can just get rid of this and then simplify it. We found alpha previously, which was 5.44, and then we're given a time interval of 5 seconds. And then we'll get 68.055 from this. We can put this in red because we want to remind ourselves that we're trying to find revolutions. And how I would do this is multiply this by 1 rev over 2 pi rads. So with that, we can cancel out that unit. And if we divide that, we would get 10.831 revs. So first I'm going to set up the linear motion for block 1. We know that net force is equal to mass 1 times acceleration, or we can expand this to alpha times r, big R. It's also equal to the downward force minus the upward force. We set these as equal to each other. To isolate for t. And then for block 2, we set up the same thing. This time, alpha acceleration will expand to alpha times little r. And then downward force minus the upward force equals to this. So these as equal to each other. Okay, and then we can go ahead and set up net torque. It's equal to the two torques being applied. So the first torque being applied is at the edge of the circle, done by the first mass. So just plug that in. And then since they're going opposite ways, I'm just going to subtract the net torque applied by the second block, which is applied at the little r distance away. Okay, and then net torque is also equal to this, which we can expand. And then set these as equal to each other. As I write this, I'm going to distribute the parentheses. And then, oh wait, this is addition. Careful of your signs. And then we want all the alphas on the same side. So I'm going to add this over and then subtract this over. And what I'm going to do as I add and subtract these terms over is take out alpha. And then we plug in all of our values. And then this will simplify to this. And then to isolate for alpha, we just divide both sides by 1.6218. And then we will end up with okay, so the new acceleration of block 1 will just be equal to alpha as it moves as a system times big R. We just found alpha, so. And then the distance would be 0.3. And then we get the new acceleration of block 1. So it's given to us that the displacement in meters is 5r, but to find the displacement in theta, we just divide it by r, so it would be 5 rad. And then I'm going to use the common form to solve for omega final, because that's what we're going to need to solve for the rotational kinetic energy of the cylinder. So we solved for alpha earlier, and then we were given the displacement, and then we can just cancel or cross that out because it starts at rest, and we're left with this formula. And then what I'm going to do is set up the KE for the cylinder to be KE rot, which is also 1/2 of inertia times omega squared. We can expand this. And then we're left with 34.338 joules. Okay, so for part H, I'm going to solve for the final omega, which is just the initial plus alpha times the time that has passed. So initial is just 0 plus the alpha times the times passed is 5 seconds. And then we would get 25.43567. And then to find the total kinetic energy, or okay, let's just start with this, right? The work done is equal to KE of the system final minus KE of the system initial. However, the initial KE is just 0 because it starts at rest. So we can just take net work to be the KE of the system after 5 seconds. So How we can do this is by setting up that the KE rot of this, actually let's just say KE of the cylinder plus KE of mass 1 plus KE of mass 2. This is equal to 1/2 IW squared because it's KE rotational. And then for both of the block masses, it'll be a linear kinetic energy. So 1/2 mv squared plus, okay. Now I'm going to expand this 1/2 mr squared, and then we have final omega. So yeah, let's just put the subscripts F, okay. And then since we only have omega right now, I'm going to turn this into omega times big R squared. And then for this, it's going to be omega times little r. Okay, and now we're going to plug in all the values. And I'm not going to round on my calculator work, but I'm just going to round while I'm writing it, so I don't have to write out such a long number for omega. And then what you end up getting is 524.63 joules.